This question is from GATE 2014 Mechanical Engineering Paper Set 1. Question number 38. A rigid uniform rod AB of length L and mass M is hinged at C such that AC is L by 3 and CB is 2L by 3. Ends A and B are supported by springs of spring constant K. The natural frequency of the system is given by. Let's see how it will be solved. So we'll start by forming the equation of motion. In order to form the Lagrange equation of motion, we'll have to find out the Lagrange term, which is equal to kinetic energy minus potential energy. Kinetic energy of the system is because of the rod, because it has mass, springs are massless. And potential energy of the system is because of the springs. Spring stores elastic potential energy, and that will consist of the potential energy. So let's find out. Kinetic energy will be equal to half into moment of inertia of the rod into omega square, its angular velocity square, because this rod is not undergoing a linear motion, it is undergoing a angular motion, and that is why the generalized coordinate that we have in our system is theta. As per the generalized coordinate theta, we have angular velocity of the rod is nothing but theta dot. Mass moment of inertia of the rod about point C, because point C is the hinged point, we'll find that out about C, will be equal to mass moment of inertia of the rod about its own center. Let that center be O. So somewhere here at L by 2, the rod of the center lies, plus mass of the rod into distance between O and C, square of it. So this is by parallel axis theorem. We are measuring the distance between the axis of the rod at O and the axis of the hinge support at C. So further substituting for IC, we have I naught is M L square by 12 plus mass of the rod M into OC can be calculated by subtracting this L by 2 from 2L by 3. That will be OC. So let's do it. 2L by 3 minus L by 2. This becomes ml square by 36, and finally we have ml square by 12 plus ml square by 36 is 4 ml square by 36, which is ml square by 9. Let's put it here. So kinetic energy K is equal to half into I is ml square by 9 and omega we already saw it is theta dot. So this will be theta dot square. We have the kinetic energy as ml square by 18 theta dot square. Now let's find out the potential energy P. Potential energy is given as half K into x square. So we have two springs here and we have spring constant of each spring is K. So let's find it out. Let's have the deflection of spring 1 be x1 and spring 2 be x2. So for each of the springs we can write half into K. This is small k, x1 square plus half small k x2 square. x1 and x2 both can be represented in terms of theta by considering theta being a small angle. We can say the arc length is equal to r into theta. So let's find out x1 and x2 and substitute. We have half k taken common. x1 is nothing but L theta by 3. So we have L theta by 3 whole square plus x2 is 2L theta by 3 again whole square. Let's simplify. So we have the potential energy as 5k L square theta square by 18. We have the kinetic energy, we have the potential energy, we can form the equation of motion. So our equation of motion can be written as d by dt of dou L by dou theta dot. So for theta dot we have only the kinetic energy term. The derivative is 2 ml square by 18 theta dot. So we can write it as ml square by 9 theta dot minus, now we need to find out the derivative of Lagrange term with theta, and only potential energy has the term theta. Already we have a minus sign with the potential energy. So we'll have the derivative as minus 5 into 2 KL square by 18 theta. We can write this as 5k L square by 9 theta. 2 gets cancelled with 18 and we get 1 by 9 here is equal to 0. Let's find the derivative further. So we have time derivative of this term becomes ml square by 9 theta double dot plus 5k L square by 9 theta is equal to 0. Now if we compare this to the standard equation of motion, we have this term is m star, that is mass equivalent, the coefficient of angular acceleration, and this term is k star, the stiffness equivalent, which is the coefficient of the angular displacement theta. So let's find out the natural frequency omega n from here. Omega n by definition is under root of stiffness equivalent k star divided by mass equivalent m star. Let's substitute these values. We have equal to root over 5k L square by 9 divided by m L square by 9. Just by simplifying this, we have the answer of angular frequency omega n as root over 5k by m. Let's mark the correct option. We have the answer in option D. Natural frequency of the system is under root of 5k by m. To learn more about Lagrange's equations, you can refer to the NPTEL video Lecture 5, Lagrange's Equations from the course of Theoretical Mechanics. It is by Professor Charudat Kadolkar. He is from Department of Physics, IIT Guwahati. I hope the solution will help you clear your doubt. Thank you.